Okay, guys, we'll get started. Let's do this one here. Diene chemistry. We've got this diene, HCl, cold temperature. We're going to form cation. Two different double bonds to react. They're not the same. First off, you're either going to put carbocation in the middle, if you recognize that. For example, if we react this alkene, we would react it with H+, we pull away from here, and we would get, we're adding UH there, and cation here. We're going to make cation on left or right here. Now it's really the same substitution, but we're going to make cation on the right as opposed to left. Why cation on the right?
They're not
Because of resonance. Yes. And if we do resonance, we'll show another cation that looks like UH there. Now here plus here. And the true structure is a blend. The blend has carbocation characteristics of tertiary and primary. We'll call this the A arrow. What if we reacted the other double bond with H+? Would we leave cation on left or right? Left or right? Left. You would also get that if you didn't even consider this because it has this group. But ultimately, the cation is going to be in the middle because it's going to have to be resonance stabilized. We react with H+. This would be the B arrow. We're coming this way. And we're going to get UH out there plus here. Then we can do resonance. And we get these electrons windshield wiper over there. And now the plus is where? There? Where the electrons left? Two different cations on the board. This hybrid and this hybrid. This hybrid is going to have characteristics of what? Secondary and what is this? Tertiary. Would you rather make a cation that has characteristics of tertiary and primary or tertiary and secondary? Yes. So at this point, we're not doing that anymore because we're going to make the lowest intermediate. Lowest energy intermediate is this one. Tertiary, secondary characteristics. Forget about that pathway. This is the alkene that's going to react. Okay, cold temperature. Which product are we going to get? 1, 2, 1, 4?
1, 2.
Yes, 1, 2. So chlorine adds to which cation? Well, there's the H. If that's 1, where's 2? Right there. Chlorine adds there. We got chlorine? Yes, this is chlorine. Electrons add there. Of course, it's adding to the hybrid. The hybrid has partial plus there. I'm not going to show the hybrid, but when we get the final product, we just have chlorine there, and so we're going to have double bond. Chlorine here. There's a new H on the end. There's your product. If you notice, this is called carbon. Is it going to be RS? Racemic. How do you attack a carbocation? from either side, right? 50-50 chance from the front or back. Planar carbocation attack from the front or back. Nothing new there. There's your product. 1,2 addition. That's what we did. That's what you get with cold temperature. What if we had done this with heat? Very next reaction is with heat. Same thing, but with heat. What product would you get? The most stable. Yes, that's what you would get. Which ones? What would you get?
Tertiary carbocation.
Well, that'd be the intermediate. What would be the product? What would be the product of the next reaction if we did with heat? Asia?
With the CO, attack the carbocation of the tertiary.
Chlorine here? Why would you say that product?
That's the most
Right here? Why are you saying that's more stable than this?
tertiary.
What's tertiary?
The carbocation.
There's no carbocation here. We judge these by the alkenes. This is a trisubstituted alkene. This is a tetrasubstituted alkene. Which alkene is more stable? Tetrasubstituted, right? Anything new there? Question?
Back when you did the first, or not that one, the one that's labeled second or second degree, up top, yeah. Why is the plus charge up at the top if you're, like, there was no original double bond? I don't see where the original double bond is that you're pulling away.
Right here.
Oh, okay. Never mind, I see now. Thank you.
This product here is formed cold or hot. Right? Questions about that one? Nada? No, it's cold because cold temperature you get the 1,2 product. This is the 1,2 product. Everybody agree? New H is here. 1,2 product. That's your cold product. What product do we get with heat? Most stable. Of the two possible, which is most stable? This one. Tetrasubstituted. That's trisubstituted. So with heat, you also get this. This is an example of the 1,2 product being the most stable. Remember I told you, the 1,4 product is usually the most stable, but not always. Which product do you get with heat? Most stable. How do you judge which is more stable? Alkene. More substitute the alkene, more stable. Tetrasubstituted, more stable. Questions? What was difficult about that? Precious? Do it? Good, good. Hopefully pretty straightforward. Okay, there's a couple more for you to do at the very bottom, and those answers are in the handout, upside down. Let's look over at the Diels-Alder reaction. Diels-Alder reaction, we're over in chapter 17. Diels-Alder reaction is a type of pericyclic reaction. Those types of reactions are classified in chapter 17. Pericyclic reactions have cyclic transition states. Diels-Alder is probably the most famous type. Diels-Alder is called a cycloaddition reaction. There's 3 types of pericyclic reactions. All this is in chapter 17. Very important, you got to be able to add 4 plus 2 equals 6. Diels-Alder gives a cyclohexene. A cyclohexane ring with a double bond, cyclohexene. Every Diels-Alder reaction gives a 6-membered ring with 1 pi bond, at least 1 pi bond. Diels-Alder reactions involve a diene and something that loves a diene. What do we call the thing that loves a diene? Dienophile. Let's look at the dienes a little closer. The simplest is 1,3-butadiene, but there will often be substituents on that. First off, we can note that the diene must be in the so-called S-cis form. Because for this carbon and this carbon, for them to bond to that carbon and that carbon, they both have to be pointed towards that alkene. Like this. Now this is a single bond. Now you may question that appropriately. But this can rotate. You may argue that it cannot. But it can rotate. This can just turn over and get like this. This is called S-trans. About the single bond is trans. It's like these double bonds are opposite about the single bond. The double bonds are considered trans about the single bond. But here the double bonds are on the same side, and that's called S-cis. To do a Diels-Alder, the diene must be in the S-cis form. Now why would I question if this could rotate or not? It's a single bond. Single bond, I can spin it, right? Why would I question that this might not be able to rotate? Because that single bond in there is some pi overlap between adjacent p orbitals. And the p orbital overlap in here may restrict the bond rotation, because if you start rotating, you're going to break that. Well, apparently that overlap is weak enough that it still rotates. I mean, that's a theoretical discussion. And the more you know about the compound, the more difficult it is to say the right answer. If you don't know anything about resonance, you say, hey, that's a single bond, it should rotate. It has to be in the S-cis form. Once you have a substituent, this double bond is no longer the same as that. We have to decide which we're going to react with, like we did up there. These guys in these rings are particularly reactive in Diels-Alder. They react faster than this. Why? Because they're stuck in the S-cis conformation. These double bonds have to be on the same side of this bond here. They cannot rotate like this. It's stuck in the S-cis. It's always ready to react. This guy rotates back and forth, and half the time maybe it's not in the right conformation. These react faster in Diels-Alder. On the next page we see the examples of dienophiles. Just your alkenes. The dienophile will typically have an electron withdrawing group on it. For example, here's your alkene, and then this ketone will be an electron withdrawing group. This helps polarize the double bond. We'll see that in a minute, consequences of that, why that's important. Presence of these electron withdrawing groups makes the reaction faster. Ketones, cyano group, esters. You can't have a cyclic dienophile. You can also have triple bonds as your dienophile. We'll see examples of these. Okay, we're going to look at some stereochemistry and then some regiochemistry. Actually, we may look at regiochemistry first because I think I repeat the same information over. Regiochemistry and then stereo. Okay. Well, I can go through this this is sort of an overview of the stereochemistry. We can see examples of reactions, so it's worth looking at this. Here's a Diels-Alder. 4 plus 2 equals 6. Your dienophile has these two esters. Of course, they're going to be there at the end. If we zip this together, boom, 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 like we showed before. 6-membered ring right there, we're making the pi bond right here. These two carbons over here are now tetrahedral. So we got 2 in the plane, 1 forward, 1 back. We have stereochemistry here. These two groups are going to be cis. Why? It's as straightforward as this. They're cis in the dienophile. See how they're cis about the double bond? If they're cis here, they're going to be cis there. Now, I'm not going to take the time to show how these react and why they end up being cis. Pretty much it's cis here, going to be cis there. As an alternative, if we take the same diene and then the trans alkene, because they're trans here, they're going to be trans there. You would zip this together. Now, we can think about it a little bit. This is a concerted reaction. These electrons just, boom, zip together. The groups have no chance to change their orientation. They're cis, boom, zip together, they're still cis. But these are now tetrahedral. We can look at stereochemistry on the diene. Here in your diene, they're both double bonds are trans, or E. That's an E double bond, that's an E double bond. So they're the same in that regard. When you zip these together, boom, 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 this comes down and makes pi bond. But over here, in this example, because this is a triple bond, when one pi bond breaks, you're left with another pi bond still there. So the use of the alkyne gives a double bond over there. Y'all see how when we zip this together, it's still one pi bond left? Boom, pi bond up here, but it's like twice the fun, one pi bond left. Now in this example, you have 2 methyls here and here. But these carbons are now tetrahedral. Where over here they were trigonoplanar. And you have potential for relative stereochemistry. These groups are going to be cis. It's as easy as this. The double bonds were the same here. They were both E. They're the same. You're going to end up with the same here in terms of cis. Again, we're not going to take time to show models and how all this happens. So it's a touch memorization here, but it's sort of the intro level of understanding Diels-Alder reaction. The stereochemistry is sort of maintained.
If they were both Z, would it still be cis?
They were both Z? Yes.
Okay.
Yeah. They're the same, so you get the same, E or Z. Now here we have the diene is E and Z. So it's opposite configuration here. When you do the reaction, you're going to get opposite here, and you get cis and trans. You get front and back. You get trans. But over here, there's no stereochemistry because that's planar. You would never draw this forward or back. Those carbons are planar. So it's understanding your geometry and structure from week 1 and 2 and your basic structure. We'll look at this again on the second page over. Let's look at regioselectivity. Not stereochemistry, but regiochemistry. Regiochemistry is looking at two totally different products. Let's see if we can predict the outcome of this first reaction. If you take this diene and this dienophile, 4 and 2, here's your alkene. Remember, electron withdrawing group makes us more reactive. We can zip these together to make a 6-membered ring with a double bond. Which do you get? Because if we zip this together like this, here, here, and here, which one do you get if this zips together like this?
First.
Yes. That gives the first one. But what if we flip the starting diene up and zip it together like that? 4 plus 2 is 6. Which one does this give? That gives the second. Now please don't think just because this is drawn down that it has to be down compared to that in the flask. This could be either way, right? So which way is going to take place? Of course, the products are regioisomers. For example, here the methoxy is bonded at this region compared to that. There it's bonded to that region compared to that. Regiochemistry. Well, this reaction is going to be regioselective. We're only going to get one of those. How do we judge? We have to look at the polarization of each. And remember that pluses like minuses. Okay, structural considerations. Your diene is the easiest. We want to look at the polarization of this pi bond. We have a dipole here. We talked about resonance. When you have a pi bond that's polarized by a heteroatom, you can just move the electrons up. And that would give that resonance structure there. First off, what are we trying to accomplish? What are we trying to figure out? We want to figure out where some plus or minus develops over here in this pi bond region, and where some plus or minus develops here. And if we can identify maybe a plus here and a minus here, then those two carbons are going to end up bonded together. We identify the pluses and minus by considering resonance and other structural considerations. Typical resonance here, polarization of the carbonyl. Can we now show another resonance structure? Particularly involving the pi bond that's reacting in this. Windshield wiper up,